Okay, so the voltage or electrical potential difference, okay, results from the separation of electrons which are negatively charged, okay? So they repel each other, right? In order to overcome this force and to push the electrons closer together, right? Right? It's just like a magnet to like if you had opposite charges or opposite poles on a magnet, you push them together, you can feel that resistance. Right? What you've done, no different actually than the exact same resistance that you would experience lifting something to a higher height. There's resistance there as well. You've created potential energy, right? It's just a different kind, right? And so when you lift an object up in the air, right, you've created potential energy by giving it height. Well, the same thing happens here, right? If we do some work and push um, electrons in this case, which have the same charge, if we push them closer together, they want to repel, right? And so if you contain them, like say in a battery, there's now this potential energy to do some work, right? They want to give off that energy that you've created for them. You've pushed them close together, right? And so we transfer this kind of energy to the electrons, which ultimately increases their potential energy. That's what a battery does. We compact tons and tons of electrons into a small space. They want to repel each other as much as they can, which ultimately drives the current flow around the circuit, okay? So the closer that we push the electrons together, right, the larger the electric potential energy that we have, right? Or sorry, the larger, potential energy. The same way, the higher I lift something, within reason, as long as it doesn't leave the Earth's gravitational field, the more gravitational potential energy it will have. Same idea. Okay, so the closer the electrons are pushed together, the larger the electric okay, and then the movement of electrons therefore requires a change in energy. Okay, much like the change in kinetic energy. Okay. And so we can see the electric potential difference is the difference in electric potential energy associated with a coulomb of charge, which we'll learn about in a minute, in case that doesn't mean anything to you. Okay, at two different points in a circuit. Okay, so this tells us how much energy has been lost or gained from one point to another across a circuit. Okay, so everything about potential is energy, right? And so we better expect, if we're using the word energy so much, we're gonna see somewhere along here, as you guys have seen, didn't matter if it was kinetic energy or gravitational potential, this is electric potential energy, all of which have units of joules, right? You better see a joule somewhere in here, right? Because we're talking about energy. Okay, so this talks about how much energy has been gained or lost from one point or another across a circuit. Okay, which could happen in any number of ways. If there's resistance, if there's a light bulb, like those are going to create, you're going to lose energy in some form or another, right? Like if it's heat, if it's sound, whatever it is. If it's a motor, an electric motor creates sound, you're going to lose energy, right? So you're going to see a decrease in electric potential in that instance across that motor, right? Because the electrons have done some form of work, right? And so a positive electric potential difference can be called a voltage gain, right? And a negative electric potential difference is sometimes called a voltage drop. Do we have any issues with that? So if we see a negative number, it means that we've kind of lost some energy, and if we see a positive one, we gained, okay? So electric potential difference can be represented by the following equation, okay? Now, you're going to see, we've already seen the letter V used for velocity. Okay, so the way I like to denote this, just to separate it from velocity, because like the thing with a capital V and a little v is there's not too much of a difference, right? So we're going to use a capital V to denote electric potential, which would be another word. You're asking why the letter V? Well, voltage. Okay, potential. So we're going to use voltage, or a capital V. But what I like to do to make sure that that's completely separate from velocity would be to put the little bars on top of the V. It's just something. You don't have to, but that's just something that I've seen in the past, I suppose. And then how do we measure the electric potential, right? Or the voltage, right? Well, we can see the change in energy per some charge, Q. Okay, so I'll write that down. So V would be the voltage or electric potential. Okay, and then delta E is going to be what your change in energy is, right? So like how excited the electrons are across your circuit, right? Like how quickly they could be moving or whatever, right? So we're going to see the change in energy. And then Q, don't ask me why we used Q for charge, but is the amount of charge measured in coulombs, right? So the amount charge, which will be measured in coulombs. I always misspell this. Coulombs. There we go. Okay. Anybody have any problems so far? So let's just jump down here. And I suppose, what's just one other thing I'm going to add here. Voltage. What you would read on a voltmeter, if you guys have ever seen one of those, that's what these look like, right? When we read like a 12-volt battery, that's telling you how much energy, we said energy was joules, how much energy every coulomb of charge has. Energy per coulomb. Okay, and I still haven't shown you what a coulomb looks like, but I'm going to show you that in a minute, okay? So let's just run through a sample calculation here, nothing too crazy, okay? So and the reason why I showed you that above is because we can line up the units, right? Again, it's not like physics is not about memorizing equations. It's about understanding where things came from, right? So the voltage would be the E over Q, right? Like that may have been shown to you in grade 9 as a memorization tactic. I don't know, right? Grade 9 was forever ago for me. I haven't taught grade 9 science. That's no different than one that I know you guys would have seen would have been something like this one, right? V is D over T. Right, but we have a better understanding now as to where that stuff comes from. When we look at the actual units, right? Like if you understand what voltage or potential is talking about, it's energy per unit coulomb, or what velocity or speed was. It's how is your position changing relative to time. That's meters per second. So it tells you what to do with the math. There's no special triangles and like covering divide this, like you know what the units are telling you to do what the units tell you to do mathematically. Okay, so when I look at this, I see voltage is the amount of energy per coulomb, and I see joules, energy, coulomb, charge. So the voltage would be equal to the amount of energy divided by the charge, right? So we're going to have 1500 joules divided by how much charge is there, how many coulombs, which again, I'll show you what that looks like in a second, 125. Right? And you should see, okay, well, that comes out to be 12 volts. Okay? So these calculations, I would say mathematically, these are some of the easier equations that we're going to use in this course. But it's when we start mixing them all together that that's where we go all sideways, right? And we forget that, voltage or potential energy is how much energy a Coulomb of charge has, right? What is current? What is resistance, right? Okay, so I'm just gonna we're gonna do 3 separate lessons to outline these things, right? So that when we deal with a complicated circuit, it's straight in our head what's going on, right? And we can use these calculations, right? So here, I think, yeah, there we go. Okay, so 1 Coulomb, I suppose, I'm looking right here now, okay? So I just want to show you guys this, because I've talked about it a number of times, but we haven't really seen what it looks like. And what I'm going to do is scroll down here and show you what Coulomb looks like, right? So 1 Coulomb, you can imagine many, many, many electrons, right? Condensed into just one package, right? And so that's what 1 Coulomb, let's say, looks like. And we know for 1 Coulomb, this is how many electrons would be in one little packaged of area, and we would call that a Coulomb. Okay? So there'd be 6.25 times 10 to the 18 electrons in this box, let's say, right? And that would be like a Coulomb of charge, right? And so if we're talking about 125 coulombs, that's a whole bunch of those. So you can imagine how you take this number and multiply by 125, that's how many electrons would be there. Okay? Now, if we wanted to figure out, we know, basically we know, how am I going to, I'm just thinking here for a second. I'm just trying to relate this to you. Let's pretend this was I don't know, a box of golf balls, and you wanted to figure out how much each golf ball cost, but you knew the total price of the box. Well, you could divide by how many golf balls were in here, right? You get how much they cost, each golf ball, right? Well, same thing here. They're not golf balls, they're electrons. How many electrons are in that box? 625 times 10 to the 18. Well, 1 Coulomb of charge is our base unit, be like $1 or something like that, right? Or the price for the entire box. This is how much. This is our price for the box, or 1 charge. If I were to divide by how many electrons are in there, it would tell me the cost, or how much charge each electron has. And you will see this come up as you guys move forward in physics. You take grade 12, you'll see that number. It's a constant. It's the charge of an electron. Okay? That's where it comes from. Each one of these little electrons has that charge. Okay? And just some of the stuff underneath here is just explaining, putting into words what I just said. Okay, so a Coulomb is like a known elementary or fundamental charge. It's the smallest indivisible amount of charge. Okay. All charges are multiples of elementary charges. Okay. Which is pretty incredible. You think that's an insane number, right? And then to think I have 125 of those. Right? How many electrons? That's crazy, right? Okay, does anybody have any questions so far? Before I jump down, we're almost done. I'm just going to jump down and build an analogy for it. Take a sip of coffee. Okay. I feel pretty good about the delivery of that. If you gave me all of it at once and you asked me a bunch of questions, I might be stuck on the equations, right? It's a lot of information to keep straight in your head. So what I want to do here is introduce this analogy. Okay. The reason why I'm so excited about this is because this is something that I struggled with in school. Like right up until I had to teach this, I was stressed about having to teach it. Like the first time before I knew this analogy. And as soon as I got shown this, like everything started to click. I was like, okay, I can keep this straight in my head. I know what the battery is. I know what current is. I know what resistance is. Okay, and we're going to build this elaborate analogy over the coming days so that we can solve complicated circuits. Okay, so we're going to build this analogy, and it's a traffic model for electricity. Okay, and we saw above what the formal definition of voltage was, right? But by the end of the unit, we're going to have to solve complex circuits with information to solve for, okay? So as you did in grade 9, but I think the circuits are going to get a little bit more complicated here, right? More information. Okay, and so here's what we got. We've got in a battery, right? And typically on a circuit, as we move through this, we're going to see batteries, and I think we saw one. Well, you'll see one this afternoon. Batteries are typically drawn like this on a circuit, right? Where we have the positive lead up here and then the negative lead down here. And these would be wires like going around and coming back again. Okay, so the negative's down there, and then the flow of electricity would follow this, and you're going to see that this afternoon in the current lesson. Okay, but what we're trying to do here is set up this analogy in terms of the battery. Okay, so the battery is like here's our battery. Okay, in the battery, or we'll call it the bank, right? If you go into a bank, the bank has vaults, right? So like big cellar doors, right? Or like vaults, right? Where they lock up all the money. Inside the bank, there's the vaults. Inside the vaults is where they keep all the valuables, right? Like jewels, valuables, right? Joules of energy, right? So when the cars come by, or the trucks, they're on their, well, you'll learn this afternoon. They come to the bank, they pull up, they go into the vaults, and they pull out the energy, joules, right? And then they take it around their circuit, and then they come back for more, and that's how this works, okay? So we're going to continue to build this analogy, right? But you're going to see that this afternoon, or when you watch the current lesson, this whole thing comes together quite nicely, right? So right now, the bank is your battery, okay? At the bank, we have vaults, or volts of potential. There's the potential to do, I don't know, there's potential to make money for taking the joules or something like that, right? And inside each of those vaults, we have joules of energy. Okay. Anybody have any questions so far? It's kind of funny. The reason why I like it too is because these match up so well. Bank, battery, vaults, volts, joule, joules. Okay, I really like this. It keeps everything straight in my head. And when we put the whole package together, there's no mixing of information, right? It's very, very clear. And you'll see this afternoon with the current lesson what that means, okay? We'll put another piece together for it, okay? Does anybody have any questions before I let you guys go? So underneath there, you got some homework questions too. Sometimes they put the answer beside. I'll see if I can find the answers. They'd be in that, I just have to find the page that this is on. And then you guys have your answer. So I'll just find the page, okay? Does anybody have